Good afternoon, everyone. Let's get started. So I have an announcement. It's kind of bad news. Today I learned that the lab in 3D22 is reserved by one section of 317 and two sections of 313 on Tuesday and Thursday from 10 o'clock to, I guess it's 2 something. So the labs are used during a big chunk of Tuesday and Thursday. I suppose that's why we're scheduled and we have our lab sections on Wednesday and Friday. So that's unfortunate because normally my class has kind of exclusive control over that lab, but I don't know what's going on this semester. So you'll have to keep that in mind if you work in the lab, that it'll be used during those periods. If you don't need the FPGA board, though, you can use on the first floor lab, 1D43. All the software you need is in that lab. Now that lab also has certain times when it's reserved. I don't know what those times are, but if you need to get into upstairs and you can't get in, you can try downstairs. Yes? Sure, yeah, and you can always work from home. You can remotely connect to the labs, or you can use the virtual machine, and I have instructions on Dropbox on how to set that up. Yeah, the only thing that you're going to need to be in the lab for is when you need the FPGA boards. We're going to spend most of our time in this class doing design and simulation, and typically the FPGAs are only used during the final step to deploy your design and to test it on real hardware. So hopefully you don't need to be in there with the FPGAs for too much time for each lab. Okay, so yeah, I'm sorry about that. I actually wasn't even aware of this until today. Okay, so today my plan is to finish my review of assembly language programming and my introduction of RISC-V. Hopefully, I don't really have a good sense of how comfortable you all are with assembly language programming. As I mentioned last week, the degree to which they cover that in 212 varies from semester to semester depending on who's teaching it and who you have. And also, it's been a while. So I've kind of rushed through this material pretty fast because I'm under the assumption that it's going to spark your memory of 212. But if any of you have any questions about it, let me know. This is a good time to ask, okay? Okay, so I talked about how our objective is to design a CPU, which is also known as a microarchitecture, and you can't design a CPU without understanding assembly language because that's the native instruction set, the native language that the CPU is executing. And so I talked about how there's several different instruction set architectures. That's the assembly language. The one we're learning is RISC-V. Hopefully in 212 you guys covered MIPS, but they're very similar. I get the sense that RISC-V was changed in the most minimal way possible to avoid getting sued. So they're very similar. And of course, if you're interested, RISC stands for Reduced Instruction Set Computer. The idea there is that the program executes a lot of instructions because they're all pretty primitive in terms of what the instructions do. But the advantage is that you can design the microarchitecture to churn through those instructions really fast, to execute them fast. So there's this trade-off between number of instructions executed per program and the time per instruction. And in the case of RISC, you're kind of going up with the instructions per program and coming down with the time per instruction in order to get performance. So RISC-V has 32 general purpose registers. You'll notice that in RARs there's also floating point registers and there's some special registers. We're only going to be using the integer registers, the general purpose registers. There's 32. You might remember from 212 that registers have they had a $sign in front of them, like $2, whereas in RISC doesn't use that. RISC uses like X2 as opposed to $2 to refer to register 2. So that's one of the things they changed. But like MIPS, the registers have these symbolic kind of aliases. So S0 to S11 are supposed to be like for local variables. T0 to T6 are temporaries that have a very short lifetime used for holding intermediate values, like sub-expression values if you're calculating a large mathematical expression. A0 through A7 are function arguments, and then there's a return address, stack pointer, global pointer, temporary pointer, and of course the 0. It's up to you. This is always a little confusing because it's like, well, what do I do then? Do I refer to the registers as X0 through X31, or do I use these special names? Well, that's up to you. I kind of go back and forth. Sometimes I'll use the X registers, sometimes I'll use these other names. You guys with me? So that's a stylistic thing. You have to decide how you want to do that. RISC-V has register 0. It's always a hard-coded 0. And okay, so today I added this slide. This is new. I thought I should have a slide here that kind of breaks down all of the different formats of all the instructions that you're going to be using in this course. And I think there's only 6 different assembly language instruction templates, or types that you'll use in this class. So the first 2 are what I call arithmetic logical shift and comparison instructions. These are number crunching instructions, compute, right? They're either add, subtract, multiply, divide, or bitwise logical operations like AND or XNOR, or comparison, set lesson, where you're comparing 2 values and putting the logical result of that comparison into a destination register, or shift instruction. And there's 2 types of those. There's the ones that use basically 3 registers, 2 source registers and a destination register, or alternatively, a lot of the arithmetic instructions, I don't know how many actually. Some of the arithmetic instructions have an immediate version where you can specify a constant instead of a register as the second input operand, right? And typically the mnemonics there will end with I, like add I, right? And then you've got your branch instructions that generally have 2 registers that are both inputs. They're compared, and then the third thing listed there is a label that you want to branch to in your code, label being a symbol with a colon in front of it, right? And so the branch, they all follow that. So you have like branch less than, branch greater than equal, right? And then there's jump instructions, which are just jump and a label, right? Those are real simple. Load and stores, these ones are the most complex because load and store instructions have different ways to address memory. But in this class, I think you'll probably just use two types. You'll either put a label, so you'll say like load word x1 and then a label, like var, or you'll have a base offset here, where you'll have a base register like x2 and an offset, like in this case 48. So it calculates the effective address by taking the contents of x2 and adding 48. Generally, when you do this addressing mode, you will have had put a load address instruction prior to this. So you'll load an address of a symbol into a base register, and then you'll use that as the base register, right? And I'll show you an example of that here in a little bit. And then there's this weird kind of instruction that I've never seen before. There's this instruction called CSRRW, which is an I/O instruction. It allows you to write to an external register. Read and write. Actually, what it does is an exchange. It reads and writes in one instruction. It does a swap. It swaps the value of two registers. One of those registers is a regular register, and the other one is some kind of an external register, an I/O register. We'll be using this instruction in this class for reading the switch values. So the FPGA board has switches, so we're going to use this to pull in the switch values from the user as a way to get input, and then we'll also use it to set the hexadecimal 7-segment displays as an output. So this instruction is, I still get confused with this one. The format is really strange though. It says CSRRW, then there's a register, an immediate, and another register. Right? And so I even forget how that works. The immediate is the special register address, and then you've got a source and a destination here. But anyway, I'll talk more about that when we come to it, but I just wanted to bring that to your attention because normally the immediate is at the end, but in this case, this one is just, I don't know what the heck that format is, this weird format. It's encoded as an R-type instruction. I think it's R-type, or maybe it's I don't remember now. Maybe it's I-type. It's encoded as a fairly common instruction format, but it just has this strange assembly language syntax. Okay, so I think all the instructions you use will follow one of those 6 formats. Okay, so let's see. Yeah, so here's an example of this load address thing. So in this case, I have a data section with something called a label in there called var, and then I've got a text section, which is the code, right? So data is your global variables, text is your code, and usually I usually put a main label here on the text, but you don't need to do that. It's going to always start executing at the first instruction in your text segment. That's what RARS does. I think if you have a main label, I think it starts with that, but I got to confirm that. But anyway, you don't need main in there. So in this case, what I'm showing here are various ways that you can load data from memory. So in the first case, I just said load word var x2. So it's going to go to var. That instruction, by the way, gets translated into 3 instructions by RARS. This is treated like a pseudo instruction because the reason for that is because the assembler will put instructions in there to translate var into a hard-coded address, a constant address, and then it sticks it into a register. The reason it requires 3 instructions to do that is because it needs to load the first 20 bits and then the second 12 bits, because you can't take a 32-bit value and put it into a register. You need 2 instructions to do that. And so that instruction gets translated into those 3. The first 2 are just setting up a base register, and the third one is the actual load. And then I also have this alternative approach where I have this load address var to x3, and that just basically, that load address just translates into those first 2 instructions there, right? And then I use x3 as my base address here. Make sense? Okay. But the first instruction and then the second and third instructions are doing the same thing. And then in this case, I have another load that uses an offset of 4. So in this case, I'm going to be loading the value of 2, right? Because var is an array of 3 words, 1, 2, and 3. Words are 4 bytes. So by offsetting by 4, starting from x3, which is the base address of var, I'm going to get the second word. Yes?
There was an issue I was running into reading input for this first lab, and it was connected with the load word, and I think it's kind of relevant to what you're talking about right now. But the error I was getting was the word isn't addressable. It was something related to the offset. So basically, I was reading input. The input was like a single integer value, like 2 or 5. And then I was trying to, I made a syscall, no problem, read that to A0. But then when I tried to load word from A0 to T0, the whole system was like, no, you can't do that.
Well, you might have been, I think in that case, you wouldn't use a move instruction. Instead of a load, because load, in order to load, you got to get it from memory. There has to be a data section. In lab 1, though, you probably don't need to use data memory. You don't need to use,
okay.
so probably.
Why that was, why it's move instead of load word.
Okay, so load word is grabbing data from an external memory outside the CPU, right? Move allows you to transfer, to basically copy the contents of one register to another. Right? So when you do the system call returns the number the user typed into register A0. No.
Yes.
I think it's A0. Okay, now the question is, do you want to use A0 or do you want to put that into another register? If you want to put it into another register, then you'll have to use a move instruction. Now this is a little confusing though, because if any of you ever write assembly language on Intel assembly language actually uses the move instruction for load and store, which makes it weird, right? But in a RISC architecture, in general in RISC architectures, that includes Alpha, Spark, MIPS, ARM, RISC-V, move is just copying from one register to another, and that's actually just a pseudo instruction that just adds 0. It just does an add with register 0. Right? But a load actually activates the DRAM or the memory system. Possibly it might hit it in the cache, right? Makes sense. So registers are the fastest memory they're inside. Basically, you can read or write a register in one cycle. Whereas any other, if you do a load or store, it's most likely going to take multiple cycles. Your program will grind to a halt and have to wait to access memory.
And when we're eventually progressing through this project, actually building the CPU, you said that there's not going to be any data memory.
Right, yeah, we're not going to, I dropped that part of the processor several years ago because we didn't have a good project that used data memory.
So does that mean that there is no way to store a word? You just have however many registers you have? Exactly,
yeah. Yeah, you're limited just to whatever you can hold in the registers if you don't have a data memory, which is limiting, but it's good enough for what we're doing for the project. But yeah, that's a great question. Yeah, we used to have data memory, and then the only project we had for that was reading an array of values and adding them up, and it was kind of lame. But then we also had another project at one point where we used load and stores to actually write pixels to a display, to a monitor, into a pixel buffer. But we dropped that one too. Okay, so let's see. So yeah, so there's a load offset 4. In this case, I do an add I with register 3. This is an addressing instruction, so I'm adding to the base register. I showed this last week where this is the way you walk through an array. You have to basically load address, load the base address of an array, and then keep adding to that base address with an add I. That allows you to traverse an array. That's fundamentally how you scan an array. Okay, and then we have this stack pointer thing. And this is kind of neat, actually. The stack is where you can. A stack is just a region of memory, and there's a register called the stack pointer, which is one of the registers, one of the numbered registers. I think it's 29 or something like that, but you can refer to as SP. And the cool thing about that is it allows you to have a place where you can just push values onto the stack. So it's used for things like local variables or return addresses from subroutines. And if you're interested in using that, it's really simple. You just basically just take the stack pointer and you begin, whenever you want to push, you decrement the stack pointer by the number of bytes that you want to push on the stack. So if you want to put one word on the stack, it's 4 bytes. You just decrement by 4. And then you just store with the stack pointer as the base address. And that's it. And then when you pop, you just add that same amount to the stack pointer. So the stack pointer grows down in address, which is a little strange. That's how it works with MIPS as well as RISC-V. But it grows down. So basically in this example, I pushed 3 words on the stack. So the first thing you do is decrement the stack pointer by 3 times 4, which is 12. And then I do 3 stores with 0, 4, and 8 offset. So they go into 3 different locations on the stack frame. And then when I'm ready to pop those off, I just add 12 to the stack. Okay. Okay. Generally speaking, when you have code, you can assume that the stack pointer has been initialized prior to your code running. So you don't have to set up the stack pointer. You just run your code and just assume it's already set up for you, that it points to the stack region of the memory space. Okay, so I also had these list of 6 challenges. I went through these kind of fast. I'll just review them real quickly here. So one of the annoyances of assembly language programming is that obviously you have to separately load values from memory, generally do your compute, and then store back. Now, as I mentioned, in this class, since we're not doing loads and stores, we're just going to get data directly from the input and then process it and then send it to the output, right? Because we're building a calculator, essentially. You can use load immediates in your code, though, as a way to store constants. So to load immediate loads an immediate into a register, right? Constant. Make sense?
Do we use li whenever we make the computer? Are we going to implement that instruction?
Well, no, that's a pseudo instruction that also gets translated to an add I with register 0. So you can do a lot with add I with register 0. You can do a move, or you can do a load immediate. Now there's a caveat there. If the immediate you're loading is more than 12 bits, then it gets translated into just like that address, it gets translated into an AUI PC and an ADI. So it depends on how big the immediate is. If the immediate is between negative 2048 and positive 2047, it'll just get, it'll just add I, right? But like I said, if it's outside that range, it'll have to be, augmented with an additional instruction to bring in the other bits. Because there's a 12-bit immediate in RISC-V. You guys might remember MIPS had a 16-bit immediate. RISC-V changed, that's one of the other differences. Okay, I also mentioned that this idea of when you have an if statement where you have to, well, you don't have to do this. There's other ways you can kind of get around this, but it makes the code even more complicated. But generally speaking, when you have an if statement, you want to have the if part at the top and the else part at the bottom. So the assembly code has to negate the comparison. So if it's basically checking to see if the if part is not going to be taken, and so if the condition of the if statement is false, which is what the branch checks, you then jump over, you go to else, right? So you jump over the then part that's immediately underneath the if condition, or in this case, the branch condition. You guys with me? So that's, I hate that. It always confuses me. But and then I mentioned when you walk through arrays, and this is just general information about RISC-V, because again, we're not going to be doing a lot of this in our hardware design. But you have to, as I mentioned, you have to directly manipulate an address register. And that's kind of related to number 4 too. And then the biggest one is register allocation. Basically just remembering what value is in each register. That's the most common cause of bugs in my experience, is just mixing up your registers. Okay. And oh yeah, and this one too. You can't compare to a constant. Can't say like if A is less than 10 without first preloading a register with 10 and then comparing to that register. Okay, so let's see, that's an example program. Let me skip over this a bit. Okay, so I might come back to that. So in our CPU, we're going to have 30 instructions, and I have them all listed there just to give you an idea of what the scope is. There's that CSSRW instruction I mentioned earlier. Notice there's no move and there's no load immediate, but those get translated into pseudo instructions. There is a load upper immediate that loads the upper immediate. That's actually, I forgot about that. So the assembler, the RARS assembler likes to use this AUIPC, which is like a load upper immediate. The only difference is that in addition to loading 20 bits into the upper part of the register, it also fills in the other bits with the program counter bits, which it's just a variation on the load upper immediate. But we're just gonna implement the load upper immediate. Okay. Okay, and then in lab, I didn't talk about this in lecture. We covered this in the lab last week. I covered it on Wednesday, and then hopefully Angela covered it on Friday. But the fixed point representation is when you have an integer and you as a programmer imagine that there's a scaling factor on that value. So you basically say, I have a value, and anything that's in that register, or I have a register, any value in that register, I'm going to assume is actually divided by 2 to some power, where the power is the number of fractional bits you want to allocate in that register. And that's something that you have to decide. Okay? So, for example, if you have a 6-bit register, and I say that I want to have 3 fractional bits, then whatever's in that register is going to be scaled by 2 to the negative 3rd power, which is 1 over 8, right? So, if let's say you have a 6-bit number and you've got 31 in that value, then that's not really 31, it's actually 31 divided by 8, right? And so that's essentially all there is to fixed point. There's different ways you can look at this. Like, for example, in this case, I have a value, and I could say, well, there's 4 fractional bits, so I'll just take the integer value of that and assume it's divided by 16, right? Because there's 4 fractional bits. And so we call that a 6-4. 6 total bits, 4 fractional, which implies that there are 2 integral bits, right? So in this case, this number is, there's a 2. In this case, I'm going to read the bits to the left of the decimal point is 2. The bits to the right of the decimal point is 13, and those, because those are all fractional, those are 1/16. So that's 2 and 13/16, right? Likewise, I could have just taken the whole value here, including all the bits, which is going to be 13 plus 32, I guess, and divide that by 16, and I'd have got the same answer. Okay, does that make sense? So what's the point of fixed point? Well, it just allows us to have fractional values in our code without using floating point instructions, because we don't want to have to implement floating point. Then you might say, well, wait a minute, if fixed point can do fractional, then why would anyone use floating point ever? It's because fixed point has a drastically reduced range as compared to floating. Floating point gives you a much bigger range because it floats the decimal point. When you fix the decimal point, you're restricted to, in this case, between 0 and 4 if it's unsigned, or -2 and +2 if it's signed. Right, that's the range of this number because of the 2 integral bits. And then the precision of this is a little harder to figure out. The precision actually varies depending on how many leading zeros you have there. So with fixed point, you can have leading zeros, which actually cause you to lose significant figures, significant bits, right, significant digits. So if you have any leading zeros, then you're actually losing precision in that number. You're losing the number of effective significant bits you have, which is another drawback of fixed point. But if you have, if you're using an application like, say, digital audio that has a fixed range, then you can use fixed point. Floating point's more for like scientific applications. Okay, so I talk about that here. Okay, so if you do a add or subtract in fixed point, you have to make sure that whenever you add or subtract fixed point numbers, you may have to adjust one of the numbers so the number of fractional bits in both values are the same. Now you might say, well, wait a second, why would that be changing? Well, because every register is going to have a number of decimal points that you're going to assume, right? So, and if you multiply 2 fixed point numbers, the number of fractional digits actually increases as the sum, potentially, if both values you multiply have more than 0 fractional bits, right? So you just have to be careful that the numbers that you add together are aligned. If they're not, you have to shift them before you add. Yes?
Is there a simple way to check the number of fractional bits when we have a value that's in a floating point register?
No, it's not floating point, you don't have to worry about it because the floating point does all that for you. That's the reason why floating point is expensive, is because it does all the denormalization, renormalization, and it takes care of the impact of adding and multiplying. But actually, floating point, when you add, it denormalizes one of the numbers and adds, so it aligns them automatically in the hardware. But in the case of fixed point, it's up to you as a programmer. You have to manually track because the hardware doesn't actually know you're using fixed point. It's all in the mind of the programmer. Okay. Okay. So let's look at an example. Yeah, let's look at an example here using fixed point. So you're only going to write 2 programs in this course that actually do something. You're going to have to write programs that test your CPU, like test code, test instructions, test benches. But there's only 2 programs you'll write that actually or have a specific purpose. The first is lab 1, which is where you're doing the square root calculation in fixed point. The second is going to be a little bit later. We're going to ask you to write a binary to base 10 conversion program, right? So because you need that anytime you use the you want to display the answer on your DE2 board in base 10, right? You want a readable number. You don't, because it's too hard to read hex, right? Hexadecimal, right? So when you do the binary to base 10, basically the idea there is that you have to have a way to extract digits, base 10 digits out of a number. And how do you do that? Well, generally you take the modulo by 10. If you have a number and you take the modulo by 10, that'll give you the rightmost digit. And then if you divide that number by 10 and do another modulo by 10, it'll give you the next digit, right? The second digit from the right with respect to the original number, right? The problem is, you might have noticed that when we looked at these list of instructions here, we don't have a divide or a modulo. Remainder, I think in RISC it's called remainder. Modulo, remainder, same thing, right? We don't have a divide or a modulo instruction. I tried to do that once years ago, but I put a divide instruction and ate up the whole FPGA because it's really expensive to do divide. So the only way to do divide with a reasonable amount of hardware is to make it a multi-cycle divide where you allow the hardware multiple cycles to perform the division. But that requires a lot more synchronization in your CPU because you have to be able to stall all the instructions coming in so you can wait and process the multi-cycle divide. And something like that is possible, but it greatly complicates the design. So we're just not going to use a divide, which is reasonable because a lot of CPUs don't have divide, a hardware divide. You have to use a software divide, implement it in software. In our case, though, we can use fixed point to get around this because we can take advantage of the fact that we actually don't need to do a full divide because the number we're dividing by is a constant, 10. We're always dividing by 10. So we can leverage that to simplify the code. And the way that I approach this is I just say, well, we'll just take the fixed point number 0.1, right? Fixed point gives you fractional numbers, right? And if you got fractional numbers, you can say 0.1, 1/10, and then you can multiply by 0.1. It accomplishes the same thing as dividing by 10, right? So that's the approach here, is that we want to use fixed point to basically divide a number by 10 by multiplying it by 0.1, 1/10. And then once you do that, if you divide a number by 10 and then take only the fractional component that's left over and then multiply that by 10, you can get a modulo, right? So for example, hold on, I've lost my slide here. Okay, so for example, if we have a number 876 and we want to extract the rightmost base 10 digit 6, right? We can take that number and multiply it by 0.1. Now the problem here though is that when you say 0.1, you have to decide what fixed point format to represent 0.1 and how many fractional bits and how many non-fractional bits. Well, that decision is going to impact your range of values, the range of values so I'm just going to say, as an example, I'm going to say 3214. So 32 bits, which is the native word size, and I'm going to have 14 of those bits be fractional bits. And so I'm going to just I'm just going to have a constant that's 0.1. Well, what is that? Well, it's basically, it's going to be 0.1. It's like 2 to the 14th power is 16,384. 0.1 would be just 1/10 of that, right? Which is 1,638, right? Go round it down, right? So that'll be my 0.1 in fixed point is 1638, right? That's 1/10 of the range of values you get with a 14-bit number, where in this case 14 is the number of fractional bits, right? So that's my 0.1. And so I'm going to take my input value, 876, and I'm going to multiply it by 0.1 by just multiplying it by 1638. So what I've done now is I've taken one value that has no fractional bits, which is my input value, because it's not going to come in with any fractional bits. I'm going to assume that I'm going to bring it in as an integer. And then I'm going to multiply it by a 32 14-bit fixed point number. So the product, the number of fractional bits in the product will be 0 plus 14. So it'll have 14 fractional bits in my product, right? And so what will happen there is I'm going to take I'm going to take that 876 and multiply it by 0.1, which is actually 1638, and that's going to give me 1,434,888, which if I then scale that by 2 to the 14th power, it should come out to be 87.6, right? It'll be 1/10. Then I'm going to mask off the fractional bits, so I want to retain the 0.6. That's easy to do because there's 14 fractional bits, and I can use an AND instruction to just extract just the fractional bits and zero out the non-fractional integral bits, right? Then whatever's left over, I can multiply by 10, again, 0 fractional bits, and that should give me 6. Hopefully. That makes sense? Okay, so let's walk through that. Let me see if I can code this up. So if we go over here to RARS, I'm just going to create a new file, and I'll say .text. Okay, the first thing I need to do is get a value in from the user, and so and you have to do this in the lab too. We need to use a system call for that, right? So to figure that, it's really easy. You go to help, you go to the help here, and if you go over here to syscalls, I don't know how easy. You probably can't read that in the back, but if I go to help, one of the system calls should be read int. That looks like 5, right? So system call 5 is read int, reads an integer from the reads an int from the input console, and it returns A0 as the integer. And in order to specify read int, specify the number, you put that into, I forget, where do you put that? A7, there it is. Yeah, step 1, put the call number in A7 right there. Okay. All right, so system call 5, so I need a load immediate A7. Yeah, A7. I'm going to stick 5, and I'm going to put a comment here that says prepare system call 5. And then I'm going to just do eCall. And that will execute the system call, so the user will type in a number there. So I'm going to put a comment there. Execute system call. Okay, then once the number comes back, it'll be in A0. So if I want, I can move that. Sorry, MV. MV is the move instruction. I can move that. I don't know if I have to move it though. I don't think I will. I'm just going to keep it in A0. So A0 is whatever the user typed in. So the next thing I need to do is load a 0.1. So for that, I'm going to do a data section here, and I'll say 0.1, and I'm going to say word, what was it, 1638, right? I also have something here called 10. That's just going to be a 10. All right. Okay, so I'm going to do, I'll do a load word, let's see, T0 0.1. So that'll load my 0.1, and then I do a mul. I'm going to multiply T0 by A0, right? So that should multiply the value by 0.1. Then I need to mask off the fractional bits, right? I just want to retain the fractional bits. And so there's 14 fractional bits. So let's do an AND, T0, T0, and then what's 14 1 bits in hex? Well, each hex character is 4 bits, right? So if I put 3 Fs, that's going to give me 12 ones, right? And if I add a 3, that'll give me 2 more. That should give me 14, right? So I'm going to do an and this, of course, it has to be and I. Hopefully that's available. Yeah, it's available. Now the problem is, though, I'm actually not sure if that's going to work because we'll find out. So that and I, that's 14 bits in the immediate. There's only a 12-bit immediate in RISC-V. So technically that won't fit, but it may translate it into a pseudo instruction which will allow me to use it. We'll find out. If not, I'll just load it from memory. Okay, so this is going to be load 0.1, multiply input value by 0.1. This will be mask off fractional bits. Okay, and then I need to multiply, then I need to load word T0, oh not T0, see, I almost screwed that up. I almost blew away my register. So I got to go to T1 because I need to retain T0. I'm going to load 10, and then I'm going to multiply T0 by T1. So that'll take the fractional part of the original value and multiply it by 10, and that should give me the rightmost digit in register T0. But it won't, because that value is still going to have 14 fractional bits, right? Because remember, the original value I read in had 0 fractional bits. This multiplied 0 fractional bit value with a 14 fractional bit number, so the product has 14 fractional bits. Then I multiplied it again by 10, which has 0 fractional bits, so I still have 14 fractional bits. So I now need to round down the value. I need to knock off all the fractional bits. So for that, I can just do a shift right logical immediate T0 by 14, and that will knock off the fractional bits, leaving behind the integral bits. Yes?
There's something I'm not understanding about the step where you're masking off the fractional bits.
Yes.
I understand, I've used a little bit of bit masks in actually 317 last semester with you, but the thing that I'm not getting is when you're multiplying T0, you're setting T0 equal to the current contents of T0 times 0.1, that's line 10, I think.
Mm-hmm.
That's an integer register, I think. So I don't understand how it's possible for there to be fractional bits there in the first place, and if so, how they're stored.
Oh, because they're in there just because of basically that 1638. I chose a number that 1638 to me is representing 0.1, because that's what the value would be if the register had 14 fractional bits. So 1638 is 1/10 of the range of a 16-bit unsigned value. 16-bit unsigned value is 0 to 2 to the, sorry, not 16, 14 rather, sorry. A 14-bit number is 0 to 16,383, right? So basically I just divided that range by 10. And so in my mind, that T0 has 0.1 in it in my fixed point representation, right? That I'm adopting, right? So there's no special hardware. I mean, from the perspective of the CPU, it's all just integer instructions, right? There's no floating point. But it works out arithmetically that it works out that way where you can where you know, basically by doing the multiply by 0.1 in fixed point and then again by 10 and then finally doing that final shift, the shift right logical that'll knock off the fractional bits and put it back into an integral, it'll convert it back into having 0 fractional bits. Mathematically, it'll work out to where it'll give me that digit, that rightmost base 10 digit of the number.
When you're doing that AND step, you're taking only the fractional bits?
Yes. Okay. Yeah, it's filtering out everything that's not fractional. Yeah, because the other bits I don't want, because I only want one digit. Okay. Like when you guys write the program that extracts all the digits, then you're going to have to retain the other bits, right? But this is just like the first step of the binary to base 10 conversion. This is just grabbing one digit.
Okay, I think I'm following you. Thank you.
So now hopefully this will work. And hopefully we don't run into rounding problems with this fixed point. Let's find out. Okay, I'm going to save it and assemble. Ah, look, I knew it. So there you go. Operand is out of range, right? So I can't, sometimes it'll translate these into pseudo instructions and other times it won't. So I'm going to go over here to my data section. I'll just have,
Can you click on settings in the top?
Yeah, but it's turned on. It says permit extended pseudo instructions. It's turned on. It's just not, it's being a jerk about this for some reason. There's no reason why it couldn't do that conversion, but.
In line 14, there's also mult instead of mol.
Oh yeah, mult, thank you. Yeah, sorry. MIPS, that's another, MIPS had mult, RISC-V has mol. It's another difference between MIPS and RISC-V. Okay, so I'm going to create something called mask.word, and I'll make it 3FFF. There we go. And then instead of that, I'll have to load word. I'll use T. Can I use T1 here again? Yeah, I think so. Yeah, T1 is not alive at this point in the code. So I'm going to load mask into T1, and then I'm going to change this guy to T1, and I'll take that I off of that and that should do it. Okay, let's assemble. There we go. Okay, so now I'm going to run it. I'm going to type in 1, 2, 3. That should give me a 3. Oh, I didn't actually output the number. Sorry. Well, that's fine. I can look at the register. All right, so the output should be in what, T0, I think? And T0 is, oh, there it is, but it's 2. It's not 3. And just to show you how to do the system call here, if I want to print that out, I need to do a load immediate. I need to do a system call. So I'm going to prepare system call. Let's go to help. System call. Print integer, that's number 1. So I'm going to load a 1. Prepare system call 1. And then I'll do a, now I also have to do a move here, because when you do that, you have to put A0 as the integer you want to print. So I'm going to do a move instruction, A0, T0, and then eCall. And that should print out the answer. Unfortunately, the answer is not going to be right, but okay, so I'm going to run that. I'm going to put 1, 2, 3, and it prints 2. Okay, something's wrong here. What's wrong? I go back and I run this again. I type 999. I get 8. Okay, well, that seems like there's a pattern developing here. What if I put 793? 2. Okay, so it seems like the answer I'm getting is 1 less than I'm expecting, right? Why is that? Well, the problem is when I did the multiply by 0.1 and then multiplied by 10, I shifted all the bits, the fractional bits, off. So I rounded down. Right? You don't want to always round down. You want to round properly, right? So the way to fix this is before I extract all the fractional bits here, I should check the most significant fractional bit, which carries a weight of 2 to the negative first power, which is 1/2. And if that bit is set, that means I got to round up. Because you should round up if it's 0.5 or higher. And 0.5 is the first fractional bit, right, in a fixed point. So, so that's easy to check. I could, for instance, I could shift it by 13 bits at first, right? Then I can do an AND instruction and check, an AND I rather. I can do an AND I to see if, after I shift the T0 by 13 bits to the left, I'll have shifted all the fractional bits out but the first fractional bit, the most significant fractional bit. Then I can do an AND to check to see if that bit is set, right? Store that value in T1. That'll be, and then I can use that to round up if necessary. So I'll go ahead and do my final shift here, shift T0 again by 1. So instead of shifting by 14, I shift by 13. I check the last remaining fractional bit, save that in T1, and then shift that last fractional bit off. And then I can just add T0, T0, T1. I'll just add that, I'll add the flag that indicated whether the first fractional bit was set. Okay, so I'll assemble that and run it. And now if I type 638, I get 8, or 678 rather, sorry. Let's put 1, 2, 3, I get 3. If I do 9777, I get 5. Uh-oh, well, that's a problem. I think in that case, I went out of range. I think that's a range violation. Let's find out. Let's see, let's do 5001. Let's see. Wait, sorry. Go back, run. 5001, got 10. Okay, so it's, I'm getting some, this is inaccurate, obviously, because I don't have enough bits. 678, yeah, 768, I got 8. So as long as I'm 3 digits, I think I'm okay. 999, I get 9, yeah. Once you get to a 4-digit number, it goes outside of the range. Now, when you do the base 10 conversion for lab 3 or whenever it is, we're going to have you use 32 fractional bits for the base 10. Sorry, for the 0.1 rather. So the 0.1, instead of being 638, it'll be 2 to the 32nd power divided by 10, which is 429 million something, right? You maximize your accuracy with that. So we've never ran into an issue with that. That's always worked for us. Okay, anyway, any questions about that? So this is a way to, basically do some fractional arithmetic with integer instructions, just using some, basically a math trick. Okay. All right. Okay, so then lab 1 is the square root lab, and I covered this in lab last week on Wednesday. I'll just briefly go over this again, because the TA talked about this on during the Friday lab, and I'm not sure, I wasn't there when she did it. So the idea is that the program, much like the program I just wrote, will ask for an input value, and we want to calculate the square root. In this case, we'll use a 14 fractional bit fixed point format. The square root algorithm, you can just use a binary search, which is the simplest way to do it. Using like Newton's method is more efficient and faster, but the binary search is the simplest algorithm I could find for this. So the idea basically is that you just start out with a guess. So you have an input value, which is s. That's the value you want to take the square root of. And then you just have a guess. You guess at the answer, and then you square that guess. And if the square of the guess is too high, you just subtract some from your guess. You bring your guess down, right? You decrement. And if it's too low, you add to your guess, right? Now the amount that you subtract or add to your guess is based on a step value. And your step value will always be divided by half each iteration through the algorithm, right? So for example, if I want to calculate the square root of 2, I can start out with a guess of 0. So if I square 0, I get 0. It's too low, so I have to add to that guess. So if I initialize my step value to 2, I would then add 2 to my guess, which the square of that is 4. Is too high, so I'll subtract half of that previous step, which is 1, which brings me back to 1. 1 squared is 1 is too low, so I have to add. Now I'm adding 0.5. Now I'm at 1.5. Square that, I get 2.25. That's too high. I subtract. Now I'm subtracting 0.25, right? You see the step is just divided by 2 each time. Now I'm at 1.25. I square that. I get 1.5625, which is too low, so I add 0.125. That brings me up to 1.375. I square that, I get 1.8, too low, I add. The step now is 0.0625, that brings me up to 1.4375. I square that, and now I'm getting close. Now I'm at 2.06, right? So I'm starting to close in, but that's too high, so I subtract 0.03125. Now I'm at 1.40625. Square that, I get 1.9775, which is even closer, but it's too low, so I'm going to actually add. That's wrong. That should say add there. But that's the idea. You basically you have an initial guess and then you keep refining it. Now, you might say, well, how in the world would you select an initial step though? I mean, you would have to know the range of possible inputs to do that. And yeah, we're gonna take advantage of that. So the reason I'm using 14 fractional bits is because that leaves 18 bits left over, and there just happens to be 18 switches on the board. So on the board, the user will flip the switches. Those will be read into the program ultimately, in your hardware, and then you can take that number and you can shift it 14 bits to the left to basically add the fractional bits, right? So that's doing a conversion, a type conversion. You're going to bring in the number as an integer, which has 0 fractional bits, because the user doesn't get the ability to put fractional bits in, we're assuming. The user is just putting a number in. The number comes in, and we shift that number 14 bits to the left, which adds 0 fractional bits, right? Which adds a .0000000 right after it. And then that number will then be in fixed point, right? In fact, you may not even have to do that. You may not even have to shift the input, depending on how you program it, because as long as your guess is in fixed point, and then you square your guess, right, and you compare that to the input. No, I take that back. You do have to add the zeros, because when you do that comparison, you have to have the fractional bits for comparing them. Yeah, so you have to add the zeros. But anyway, that's the algorithm, right? Now for debugging it, I have a spreadsheet on the course page. If you go to Dropbox, there's a download here called Binary Search Spreadsheet. So this is an Excel spreadsheet that implements this algorithm. And it's useful for debugging your code. If it opens, come on, buddy. Yeah, it's not. Well, it's not opening. I might have lost. No, I'm online. How about refresh? Let's do save link as. There we go. Oh, that's why. It's a security thing. We want to keep that file. There we go. That's why it didn't work when I clicked on it. Okay, so you open this thing, and this allows you to type in the number you want to take the square root of at the top, and then this just shows you the progression. Now, the idea is that your step value is divided by 2 each time through, so you just shift it by 1 bit. So basically, you start out your step as a 1 in the most significant bit. I think. It's 128. So it's 128 is 2 to the 7th, and you have 14 fractional bits, and 7 plus 14 is, so I guess it's bit 24, I guess, actually. So it's basically 128 shifted 14 bits to the left. That's your initial step. And then each time through, you just shift it to the right by 1 bit each. Because you guys, shifting to the right, you guys know that divides by 2, right? Okay, so the switches, if you put all the switches up on the board, you put all 18 switches up, that's going to give you a value of 2 to the 18th power minus 1, which is 256K. And if you take the square root of that, it's just under 512. So you know that the answer has to be between 0 and 512. And that's the reason why your guess starts out at 256, which is half the range, and then your step value is 128. Make sense? Okay, so let's see, let's enable editing, and then, so 500, square root of 500, I've got calculated 22.36072, which is not exactly right. It's actually off by, the error is 0.00004 in terms of the square root is off by that much. So there is, there's limited precision with the algorithm. You can get within 2 to the negative 14th power, right? Which is roughly 10 to the negative 4th power, I believe, right? Make sense? Okay, so this basically the code is it's a loop. You have to build a loop in the assembly language and in the assembly code, and then it's that loop is maybe 20 instructions. It's fairly short, but tricky to debug because it's assembly language. But remember, you're working on this project in teams of 2, so you have a group of 2, and only one member of the group even needs to submit it, and both members receive the same grade. So make sure you pick your lab partner soon. If you don't have one or you can't find one, send me an email, and we'll find you someone. Okay. The lab sheet's on there, and then the input value comes from the terminal in this case. Eventually, we'll use this program on the board once we have the CPU. But for now, we're just running this in RARs. Okay? Any questions? Yes?
The 0.1 number you said was 1638, right?
This one, you don't need 0.1 for this one. The 0.1 is only for, that'll be for the next program you write, the base 10 conversion.
Yeah.
I just use that as an example.
I just wanted to clarify from my understanding. That means that if you divide that number by 2 to the 14th
Mhm.
it'll be 0.1.
That's right. That's exactly right. Yeah, it's a scale. You have a scaling factor associated with that value. That's what it is, which is 2 to the, you're dividing by 2 to the power of the number of fractional bits. Yes.
Why is the guess set to 256 here?
The guess is set up to be halfway in between the smallest answer and the highest answer. So the smallest answer you're going to get is 0. That's if you give it an input of 0. The highest answer is going to be 511.99999, right? Which is if you give it the maximum value. This is in terms of the board, right? So basically, the initial step and the initial guess are values that we've chosen that are tied to the board, not to RARs, right? So basically what this means is in RARs, when you're testing your code, if you type a number in greater than 2 to the 18th power, which is 256,000, right? So if you put 300,000, it'll break the code. It won't give you the right answer, right? So but we're giving these values because we plan to eventually use them on the hardware, right? But so this is going to limit this algorithm to only working for a value between 0 and 2 to the 18th power,
So
minus 1.
because of the fractional bits that we've chosen.
That's right, yeah, and the initial step, because that initial step is the highest value you can take this. The highest you can go here is by essentially always adding. If you take your step and always add it, add, like if these are all adds, right? In fact, we can try it. So let's say we do 300,000 here. So this is going to fail pretty miserably. So the error was negative 35, right? Now the error should never be that high. So what happened here is when I put that number in, it always added. The direction is U, means up, right? Which means it added. So we started with 256, but basically we kept adding, but we kept adding a number that we're having, right? So we asymptotically approached 512, right? But there's no way for this answer to get beyond 512. It's going to infinitely approach that, but never hit it, right? And so in this case, we got the 511.99988, which is the largest number that we could output based on that guess and that step. Yes?
So you were talking about how division is pretty tricky, but in theory, could you take the initial guess and divide it by 2, like if you were able to write that code, and then just make that the initial step size, and then would that be more accurate?
Sure. Yeah, it'll save you some steps. Yeah, that would save you. You wouldn't have to iterate as long if that would give you a better initial guess. Yeah. Some people, you're welcome to do that. That's no problem. You don't have to use this. Well, as I mentioned, I mean the guess and the step are designed for this range of values, 0 to 512.
Like
but
in terms of if you were to input a number out of the range that we're looking at, because then if you were to go up every single time.
Oh, you're saying that would improve the, that would also get you outside that range. Yeah, so let's say I type 300,000.
Yeah.
You're saying start at 150,000.
Yeah.
Yeah, but you'd still be limited by the step, the initial, you can set the initial step to half that though. Yeah, that's a good point, sure. Yeah, that's a way that you could get outside this range. That's a good idea. Yeah, that would work. But you don't need to for this lab.
Because the board wouldn't support that.
Yeah, but that's a good idea. The dividing by 2 is not a problem. You can always just shift. Like if you're dividing by a power of 2, that's easy, right? You just shift. You can use a shift, right? Likewise, if you're multiplying by a power of 2, you use a left shift. Dividing is right shift. So yeah, that worked. Okay. Any other questions? Oh, one other thing. Two things about this lab though. There's 2 tricks here. One is, if you type a number in that is a square, like say 25, you have to make sure that if your square of the guess is exactly the number entered, you have to bail out, because otherwise you'll miss. You'll get the answer, which in this case is 5, right? But then you leave the 5 and you end up with 4.99988, right? So make sure that you check for that in your code. And the other thing too is when you have 14 fractional bits in your guess and you square it, The answer is going to have 28 fractional bits, right? Because it's 14 fractional bits multiplied by 14 fractional bits. You're going to have 28 fractional bits, right? Which only leaves 4 bits left over for the integral part. Right? Was that enough? Well, no, because remember, the user is putting in a number between 0 and 256,000. So 4 bits isn't enough. So when you do your multiply, when you square your guess, you need all 64 bits of the result. Right? Now how do you get all 64 bits of the product? You have to use the mul h instruction, actually the mul hu instruction, the unsigned version of it, which just does the multiply and gives you the upper 32 bits, right? And then you have to, obviously when you do the shift, when you shift by 14 bits to knock off those extra fractional bits, you need to then combine those two words together. Does that make sense? You can do that through bit manipulation, right? You're basically just using ORs to combine two values together, right? That's really that's probably the trickiest part of the project, is that part where when you do the x squared, you have to make sure you hang on to all 64 bits. And that's the reason why we have you implementing later. We're going to have the mul hu instruction. So if you look at these listed instructions again, we have add, subtract, multiply, multiply high, which gives you the upper 16 bits of the, because if you multiply two 32-bit numbers, you need all 64 bits of the product. So multiply high gives you the upper 32 bits, and multiply high u is the same thing, but it's the unsigned variant. And this project is unsigned numbers. There's no negative numbers. So make sure you use the mul hu. And then we have add I, set less than unsigned, and or XOR, and I, XOR I, or I, XOR I, the shifts, load up or immediate, IO instruction, and then some branch and jumps that we add in the next lab, the second lab. Okay, so the reason why we have these two is because to support this type of fixed point. When you do fixed point, it's often the case you're going to need all the bits of the result. Okay. Alrighty. Now I have some examples here. I don't know. These are probably a little too complex though to I was pretty proud of these when I came up with these last fall, but on revisiting them, they're pretty they're a little hard to cover here. But the first example, I'll just give you a quick rundown of these. By the way, these programs are available on Dropbox if you're interested in looking. But basically, the first program is to calculate the sign of a fixed point number using a Taylor expansion. A Taylor expansion, or Taylor series rather. Taylor series is a way to approximate an arbitrary function if you know the derivatives of that function at a specific point, right? So in this case, A is that point. And so this works really well for trigonomic function, or sine anyway, because sine of 0 is 0, but then the derivative of sine at 0 is 1, because its derivative of sine is cosine, right? And then the second derivative brings you back to sine, is 0. So what you end up with is this, as you calculate the first, second, third, fourth, and so on derivatives of sine at 0, it basically just alternates between 0 and 1. And then A, of course, is 0, so basically the x value is the value that you want to evaluate it at. So anyway, this is the Taylor expansion. So sine of x is the sine of 0 plus the cosine of 0 over 1 factorial times x minus 0 minus the sine of 0 over 2 factorial times x minus 0 squared, and so on. And in this case, we stop it. We stop the factorial at 13 or so, because that's the highest factorial you can fit in a 32-bit number. So that's basically the idea. And so I've got a program. I did it in C. This is the C implementation. So there's a function called mySine. I called it mySine so it wouldn't conflict with the regular sine function. And then my exponentiation, and then my factorial. And then you can see it's a fairly simple program. And then I convert it to assembly language here, along with including the corresponding lines of C code and how I translated them, so you get an idea of how that works. And then I also have a merge sort program. This is we did a bubble sort, or I did a bubble sort in the Wednesday's lab. Angela did a random number generator in Friday's lab. But this is a merge sort. It's a little bit more complex sort. And basically it does a divide and conquer. And again, I have the code here for it as well as the assembly code. So you're welcome to check that out. The programs are available, like I said, to download and try them out on the Dropbox. All right, so that's my whole introduction or review, introduction to RISC-V and review of assembly. Hopefully you guys are comfortable with that. We'll be in lab as you work on this on Wednesday and Friday. Oh, the due date, by the way, is September 10th, I believe. September 11th. Sunday, September 11th. The reason I make it Sunday, just so you guys know, just so you don't think I'm just being a jerk about this, I always make these due on Sunday because if I make them due on Monday, then no one comes to lecture because they're still working on the lab, right? I found that out the hard way. So Sunday, it has to be due before the lecture, otherwise no one shows up. So that's the reason. That's the reason for that. So you've got, like, I guess, 2 weeks essentially to get that done. Okay, sounds good. Thank you.